Okay, this lesson is number 22 and it's on logic circuits. What we're going to do is look at some of the features of your circuit board. We're going to do 2 experiments here. Actually, you'll do 3, but I'm going to show you everything that you need to see about the circuit board, and then I'm going to the whiteboard to draw a circuit and that you'll need to draw. So we're going to look at some of the simpler things first. In the upper right hand corner we have this area called logic indicators, and the way that works is if there's a high voltage or a low voltage, then we have either a red light or a green light on. So what you're going to end up doing is connecting to the positive voltage because we do want to vary the voltage. And notice I have this, the knob that controls the positive voltage, I have it turned down. So the idea is you can just take this wire and you put it into the first row. So the first row goes with indicator 1, there's the green one and the red one that both go with indicator 1. And so there's a set of 8 of those. Now the green goes with low voltage, and you're actually going to use your voltmeter connected from ground to here to measure some voltages, and it kind of tells you that. But I'm just going to show you what you should be seeing. You notice that the green is on. As I turn this up, the green goes off, and then as I keep turning the voltage on, the red comes on. So it's best not to turn it all the way around to the high 15 volts. I'm not sure if that will burn anything out, but we don't want to do that. So the first experiment is using these indicators. The first part has you to find the voltage when the green one goes off and the red one goes on. So you'll be using your voltmeter and you'll measure some voltages. There's a place for you to record the voltages and then some questions about that. Okay, so that is what you're going to be doing for the first experiment. And then we're going to use a different area. Actually, we're going to still use this area, but we're going to use the lower left region. And I have no idea why they put these switches diagonally opposite from these. They should have put them like right under each other, but they didn't. So now I'm going to take this wire out because I'm not going to apply the voltage with the voltage here. So the switches over here in the lower left-hand corner will supply enough voltage, a high voltage or a low voltage, to light one or the other of the lights in the indicator. So there's a note that I wrote in here. There are a lot of these wires that are grounded and connected underneath, because if you notice, when I had this, I just had a wire from the yellow terminal to the holes here. So it looks like this is sending voltage to here. That's not the way voltage works, and you should remember this from almost everything that we've done from the beginning. Voltage is a potential difference between 2 points. Current is what flows. So there are things connected underneath that we don't see. So I guess I just wanted to mention that. Okay, so to use a switch, I'm going to have to use a long wire, and these go by columns. So the first column is the first switch, and the switches are not directly underneath the circuit board here. So they are numbered, but the first hole, first column, goes with switch 1. Notice I've got switch 1 down, and then I'm going to put it over here into logic indicator 1, so I'm in the first row. And notice what happens. We have a green light that comes on. So with the switches down, that's low. Now, if I move switch 1, so you have to remember to count over here and find switch 1. It's not the switch that's directly under this. So switch 1, if I move it up to high, then the green goes off and the red comes on. So that's kind of how those work. A couple of other settings that I forgot to mention but are in the lab. For the indicator section, there's a little switch up here, needs to be on the plus 5 volts because then it is connected to the fixed 5 volts. If we connected it to the plus V, then it would connect to this and we could actually set a voltage, and we're not going to do that. So for the indicator region, this needs to be in the up position for the plus 5 volts. It also needs to be in the CMOS position. The TTL is a different thing and we're not going to use that. The same thing over here, there's a plus V and a plus 5, so we're going to have it in the plus 5 position. Now, the experiment that you're going to do with this is not really very complicated. I was trying to figure out what kind of an experiment can you do. So I decided that what I would have you do is you can connect different sets of these logic indicators together. So I'm going to have you to connect all of the odd ones together, and then they're going to be controlled by this switch. Now, we could have different switches controlling different ones, and there's lots of combinations of things that could be done, but I kind of decided on this little bit simpler one. So I'll show you a little bit. So if we want to connect switch 1 or indicator 1 to indicator 3, you just simply put a wire in row 1 and then you put it in row 3. And so, of course, the indicator 3 comes on. Again, if I put my switch back down to low, then both of the green ones come on. So the idea here is that you're going to use switch 1 and switch 2 to connect to the different indicators. And I've got switch 1 that's going to be connected to the odd ones, and so you'll have to use more wires there. And switch 2 will be used to connect to the even ones. And then I have a few questions about how do you position the switches to get the various ones to come on or be off. So that's the second part, and that one's really pretty easy as well. When you do this one, you are going to have lots of wires there, so I don't know, you'll just have to make sure that you get things in the right places. Okay, now the last part is going to be using the MOSFET transistor that we used before. So I would recommend take all the wires off, whatever you have on there, take it all off of there, and then we'll start. And I'm not going to connect the whole circuit because I don't have it drawn on the board yet, but I'm going to show you the relevant parts. You need the transistor. The black side should be facing to the right. Since you're going to be using voltages over here, I would recommend doing it on this side as opposed to over there. So just put it in there anywhere. And then you're going to have a resistor, which I did have. Oh, it's right here. It is brown, black, red, 1 kilo ohm, and I do believe that you should have this. If you don't have this, you might email me and let me know. Something else very close to that would be all right as well. So I'm going to put the resistor in here. Now, the thing you have to go back, and I will draw it on the board too, is to keep track of which of the 3 pins is which. Remember, with the MOSFET transistor, there's a source, a drain, and a gate. So this resistor must go to the drain, and the drain happens to be the middle one. They did not arrange these the way I think they should have, but they didn't ask me when they built them, so Okay, so I'm going to put that there, and it's going to go up here. And then this is going to go to the red positive 5 volts, so you'll have a wire going up to here. And as I said, I'm not going to connect to everything because I want to get it on the board, and you've got experience at setting up a lot of these circuits, so you should be able to do fine. Okay, then the source is the top one, and it's going to go to ground, so you can have it up here to ground. The gate is the lower one, the one down here, and it's going to be connected to this positive 15 volts. Now, you're probably not going to have 15 volts, so I would recommend always, if you're using either the yellow or the blue, you should turn both of these knobs down so it's low voltage, in case whatever you're hooking it up to can't really have a higher voltage. So there's a yellow, the gate, which is the bottom one, will be connected to the yellow terminal here, and then this knob here is the one that controls that. Now, you're going to be measuring voltage across 2 places, and one of them is the drain and the ground. The drain is the middle, so the middle to the ground. You can have it up here or down there. And then you're going to be measuring the voltage also from ground up to the yellow voltage here. So that's going to be the input voltage. Okay, so that's, you'll have this, and then both of your meters. And when I put the circuit on the board, I'll show you, I'll kind of recommend which meter to use where. But you're going to be measuring 2 voltages, so it doesn't really matter which meter you use in which place. So now I'm going to go to the board and draw the circuit, and then there's a derivation that I need to do. So we'll go to the board. Actually, I want to turn this off. Okay, the first thing I'm going to do is to draw the picture of the transistor. So this is the black side facing you, black side out. Black side always goes to the right side when you put it in the circuit board. And it has 3 legs. I think these are usually called legs or pins or leads or something. So the top one is the source, the middle one is the drain, and the bottom one is the gate. And on this one, it's not that easy to bend these legs. On the small transistor, it was convenient to bend them out a little bit so they're separated. These seem to be a lot stiffer, so they're not that easy to bend. So I would just recommend just putting it directly into the circuit board. Okay. So I'm going to start here, and I'm going to start at the top with the plus 5 volts. Be sure it's the positive 5. It's fixed at 5. You can't do anything about it. This is also the red terminal. Okay. Then we're going to come down and have a resistor, and I'm going to call this the drain resistor. So a subscript capital D. And as you'll see in here, this is the circuit that's in figure 10.11. It's on page 138 in the book. I've added a few things, hopefully make it a little easier to understand. But this is basically what's in the book. So then we're going here to the drain of the transistor. And we have drain here. The bottom one is the source. And notice that in the picture, these are not arranged in the same way, in the same order that they are on the actual transistor. So that's the thing that was kind of confusing. Then this goes to ground. And as you should remember, the lower left-hand corner B and C ground is a ground just as well as the black one in the upper right-hand corner. But since we're working in the upper right-hand corner, normally we just go to the black terminal in the upper right hand corner. Okay, so the gate is here, and you should draw an arrow on it. I guess it doesn't make a lot of difference, but that makes the symbol complete. So there's the gate, and then this goes up to the positive 15 volt terminal. Now, it's not a fixed 15 volts, but it's a lot easier to just put 15 volts than to put the 1.3 to 15. And this is the yellow terminal. This one is called VIN. And let's see. Oh, we need V out. V out is over here. So you're going to measure V out, and that should be measured relative to ground. So what I would recommend is I'm going to put this, so that's the voltmeter, positive side there, negative side over here. I'm not going to actually draw it attaching to anything, but obviously when you put it there, you're going to have to do that. So you can attach it to ground, and then this needs to go to the drain, or it can go to the side of the resistor that goes to the drain. So as long as it's in that vicinity. Now, the other voltage, VN, is measured from ground up to whatever voltage that is. So it will go to the yellow terminal. So there's the voltmeter. This is positive, negative. Oh, and over here, I would suggest that you use the orange meter here, orange, EMM, and use the yellow one over here. Although, as I mentioned earlier, it doesn't really matter which one you use where, because you're both going to use them, or you'll use both of them for voltage, and I might as well tell you here, I don't know if I put it, I don't think I actually put it in the write-up, but this should be set at 20 volts DC, nothing oscillating here, and this one also at 20 volts DC. Because you will have a few voltages, probably about 5 volts is the highest you'll have, but since the setting below the 20 is 2, then it's going to be more than that. And it's also best if you pick a scale and keep that scale for all of the measurements. If you remember back in the first 1 or 2 labs, I had you to measure a voltage on one scale and then on another scale, or resistance or something. You had to measure something on a couple of different scales, and you remember that you did not get exactly the same thing. You get very close, but that's why it's better just pick a scale and use that one for the whole experiment. Okay, so this is the circuit that you should draw. It's on page 184. And then the question is, a couple of things. It says to vary the input voltage from 1.5 to 5, because we really don't want to go more than this. It's not good if this voltage is larger than this voltage. It's a little bit larger, that's okay, but basically we're going to vary this from about 1.5, since it doesn't go to 0. 0 is 0, I guess, but the lowest you have is usually about 1.2 or 1.3. So I thought, well, let's just start at 1.5, and to increase this voltage in increments of 0.5 volts. Okay. Now, I will tell you what's going to happen. When you increase this, the output voltage is not going to change very much for the first few measurements. And then you're going to notice that this voltage changes very quickly and a lot within like from one measurement to the next. So what I've said here is that when V out is changing slowly, then use increments of 0.5 volts here. When you notice that this voltage, the output voltage, has changed a lot for your next measurement, then go back and go in smaller increments, maybe increments of 0.1 or maybe 0.2 volts, just kind of to get a better set of readings in the region where this changes quickly. So then the last few, after this is changed, then it's going to kind of settle down and not change very much. So I did not tell you specifically. One reason is the transistors don't all behave exactly the same as far as where the different voltages are. So the idea is for you can kind of figure out what numbers or what sort of data that you want, and that will be good. So to begin with, you'll have it changing at 0.5 volts. In the middle part, it'll change by 0.1 or 0.2. That's what you should do. And then at the end, it'll settle down and you can change back or go back to changing in increments of 0.5 volts. Now, the reason for this is what we're after here is to figure out what is called the channel resistance. So I didn't really say very much about the actual construction of these MOSFET transistors. I did a little bit, but there's also more in the book if you want to read about it. But there's a channel, a conducting channel that appears, and what we would like is the resistance of that. Well, it should be kind of obvious that the resistance is not going to be the same kind of resistance as you would have with like a 10 ohm or 50 kilo ohm resistor. So it's not going to be logical to try to measure the resistance with an ohm meter. Okay, well, if we don't measure it that way, then how are we going to measure it? So we decide, well, we have some voltages, and we have some other resistors, and we have this little technique that we learned at the end of lesson 6 called using a voltage divider. So I'll go through that derivation in just a minute, but I wanted to explain a little bit more here. So what you're going to end up doing after you have the data for Vin and V out, then you're going to use the equation that I'm going to derive, and you will calculate the channel resistance for each of the sets of voltages. And then you'll end up plotting a graph of resistance, the channel resistance, versus the gate source voltage, which is this, and that's the Vin. Okay, so, and it tells you this. So you'll have a graph. And I've got a few questions in there about what does the graph mean, or what do you think the effect is. I'm not going to say much about those because I want to see if you can come up with some ideas. And remember that we're in the section on logic. So we have high and low voltage, or on and off, zeros and ones, all kinds of things like that. Now, I do have a question in the homework about a P channel. I should mention, and I've mentioned this before, this is an N channel. It has to do with the charge of the particles in the channel. If you get negative charges here, or if you get the positive holes. So actually they're not positive, but they behave that way. So after you get the graph for the N channel, then the question is, what do you think the graph would be for a P channel? And we can't do that because I didn't find any P-channel transistors when I was looking for them, and so I decided, well, the N-channel would be sufficient. In the book he says, and if you read about P-channel and N-channel transistors, they're what's called complementary. So that might give you a hint as to what a graph of resistance versus voltage for a P-channel might look like relative to the N-channel graph. So there's just a couple of questions in there about that. Okay, so now what I need to do is to show you, and I think what I'm going to do is I'm going to show you how we start the equation, and then I'm going to erase this so I'll have room to actually do it. Well, if you think back to the voltage divider, it's basically a ratio of voltages and a ratio of resistances. So the ratio of this voltage, which is V out, so I'll put it up here, V out, to the total voltage from ground up to the 5 volts, so obviously that's 5 volts, is equal to the ratio of the resistances for the same regions. So the resistance for this transistor, I'm going to call it R with a subscript CH for channel. So it's the channel resistance. So that's the numerator. Then the denominator is the channel resistance plus RD. And remember, we have resistors in series, just simply add as they are. So we're going to have that divided by RCH plus RD. Now we have a value for RD. Oh, I was going to put it up here. It's 1 kilo ohm, and that is the brown, black, red. Brown, black, red. Okay. So the theory is from algebra, if you have one equation with one unknown, you should be able to solve for it. The unknown that we have is the channel resistance. We know our voltage out. We have several of those, but we have that value. We know the drain resistor, so we should be able to solve for the channel resistance. So rather than do it individually for each of the sets of voltage, we need to go through and get an equation for the channel resistance so that we have it on the left side and everything else on the right side. So that's what I'm going to do here. Okay, so the easiest way is cross multiply. That's the first step. And there's space for you to write this. You really should do this. So we're going to have V out times R channel plus R drain equals, cross multiply the other way, we have 5 times R channel. Now we need to remove parentheses, and for my students, when I used to say remove parentheses, they would grab their eraser, and I said no, it's not erasing it, it's multiplying it out. It's mathematically removing it, not physically removing it with an eraser. Okay, so we have V out times R channel plus V out times the drain resistance is equal to 5 times R channel. So now we have R channel in 2 terms, so we have to get them to the same side of the equal sign. And what I'm going to do, I want to leave this on the left side. So V out times the drain resistance. And when I move this to the other side, I'm going to factor out the channel resistance. And then we have a 5 here, and then when this term goes to the right side, it becomes a minus. So we have minus V out. Okay, we want to solve for R channel. So I like that on the left side, so I'm going to move it to everything, just switch sides. This is going to be V out times the drain resistance divided by 5 minus V out. Okay, so that all goes in parentheses. Okay, so what you're going to end up doing then is for each set of, for each position, you have a voltage out, and you simply put it in here. Make sure that you do the arithmetic right with your parentheses and things like that. Some of you have to watch. If you don't get your parentheses in the right places, then things don't turn out right. I will tell you ahead of time that your first one or two of these will be very, very large, and then you will have some intermediate ones, and then you will have some very small ones. So if it doesn't turn out quite like that, you might let me know. And since this is 1 kiloohm, then you don't, actually this is really all you need to do from the arithmetic point of view, and then times 1. But then your resistance, actually on here I just have it as ohms. So you might change that to kiloohms. I might actually change it before I post this. I haven't posted it yet. But you should watch for the resistance and make sure you get the units right and the power of 10. Okay, so this is the equation that you're going to use. Okay, then after that you'll plot the graph, and it'll probably look like no graph you've seen before. And as I said, there's a couple of questions about it. On the homework, there's one problem where you have to calculate the channel resistance. I basically give you this information, and then you have to calculate this. So it's the same kind of calculation that you've done.